exponential functions. So we'll learn how to graph exponential functions, simplify, and calculate exponential functions. Okay, so start off with the definition of an exponential function. If you're given an equation, f of x equals a to the x, where the base of the exponential function is greater than 0 and not equal to 1, this defines an exponential function with base a. The domain of an exponential function is the set of all real numbers, negative infinity to infinity, and the range of an exponential function is a set of all positive numbers 0 to infinity. All graphs will pass through the point 0, 1, and the graphs are continuous curves with no holes or jumps. The x-axis is a horizontal asymptote. We've seen those before. And if the base is greater than 1, then it is an all-increasing function. If the exponential base is between 0 and 1, then it is an all-decreasing function. Okay. So let's go ahead and look at 2 to the x, the graph of 2 to the x. We're going to graph it, state the domain, range, and the horizontal asymptote. Okay, so 2 to the x, let me see. We can probably use Desmos, why not? Boom, boom. Let me hide this, hide video, and then hide floating. There we go. Okay, and I'll type in 2 raised to the x. All right, and I'll do my table. I'm going to type in these numbers that we have on the right side. So -3, -2, -1, 0, 1, 2, 3. Okay, and fill out the rest of my chart. So we get 0.125, 0.25, 0.5, 1, 2, 4, 8. Okay. And maybe I can make this graph appropriate. How about just -10 to 10, and then y, we can start at 0 and go up to 10. Why not? All right, so this is what our graph's going to look like, but of course we'll graph it over here. So we're going to plot those values. Let me make this, that's 0, 1, 2, 3, -1, -2, -3. So we said at -3, we were at 0.125. Let me leave that one up. We were at 0.125. So that's going to be barely above the x-axis. We'll say right there. Oh, I can make that a little smaller. Okay. Right there. And then at -2, we're at 1/4, so not much higher than the last one. And then at -1, we're at 1/2. And then 0, we're at 1. 1, we're at 2. 2, we are at 4. And 3, we are at 8. 5, 6, 7, 8. So here is what our exponential function of 2 to the x looks like. Okay, and no matter how small the x values get, you will never, ever touch the x-axis. You'll just get really, really close to 0, but you will never touch. And you can show that by the XY chart. Let's say if I chose -10, I get 9.76, what is that, times 10 to the -4. So that is a really small number. I could even show it by the graph that we have in Desmos. Let's say I want to zoom in at -10. It looks like we are on the x-axis, but if I zoom in enough, it shows that we are not even touching the x-axis. We will never touch the x-axis. So you're going to get really close to 0, but you will never touch it. That's why we say exponential functions have a horizontal asymptote. Okay. So let's go ahead and draw that horizontal asymptote then. So that's just going to be right here on the x-axis. There it is, y equals 0. Okay. Let me come back here. So there's the function 2 to the x. Our domain, as stated by the properties above, the domain of any exponential function is the set of all real numbers. The range of a common or a basic exponential function, such as 2 to the x, is going to go from 0, oh, that's sideways, 0 to infinity. And our horizontal asymptote, from what I just drew, is going to be y equals 0. Okay. Any questions on that?
No, sir.
And now, here are the rules of exponents. We saw them last week. We refreshed on our exponential rules. So these are just stated again, so we know how to handle exponents when the time calls for it. So remember that same base, you add your exponents, and then power to a power, you multiply your exponents. Anything raised to the 0th power is always 1. Same base dividing each other, you will subtract your exponents. And then product to power, if you have a times b raised to the x, then you can make it a to the x times b to the x. And then our negative exponent rule, a to the negative x can be rewritten as 1 over a to the positive x. So these are all the rules we saw on Thursday. So just stated again to help us out. Okay. Next is evaluating exponential functions. So all we want to do is plug these into a calculator. We want to evaluate the exponential expressions. So why not use Desmos? Okay. So first up is 4 cubed. So 4 and raise it to the 3rd. We get 64. So this gives me 64. And then 2.5 raised to the 7.1. And we'll do this to, let's say, 3 decimal places. We get 668.919. Or that can even 0.920. Why not? Okay. And then 3 to the negative 2. 3 raised to the negative 2. We get 0.11 repeating. And then 1/3 squared, we get, I can type it in exactly like that, parentheses, 1 divide 3, move that over, and square it. And again, we get 0.11 repeating. So for my math lab, it probably doesn't let you do the repeating symbol. So it's probably going to do 2 decimal places or 3 decimal places. So for my math lab, put it at 0.111, or maybe just 11, depending how many decimal places it asks for. Okay, so that's plugging into the calculator. Not bad. Any questions on that one?
No, pretty straightforward.
All right. Maybe I'll keep Desmos up for the rest of this. Let's see. Yeah, because we're going to be plugging in our calculator over here. Okay. Okay, so next up is the exponential base of E and where it comes from. So this exponential base of E has been used for, it's been around for a very long time, and it's used in science applications and business applications. And we'll start seeing that once we get into the chapter 3. But so what E does, E is it's called a natural exponential base, and it also occurs in nature. That's why we said science. This base of E can help you find the growth rate or decay rate of a certain animal population. And if that can be said, then it can also help you find the growth and decay rate of an investment. So E is used a lot, and it's pretty awesome. So where it comes from, well, it comes from this expression. Let's zoom in here. So the definition for E says, as H is greater than 0, and as H approaches infinity, the expression 1 plus 1 over H raised to the H will become the number E. So somebody created this expression, and his name is Euler, or it looks like Euler, but Euler, so it's Euler's number. And this expression, if H keeps getting infinitely larger, will start to approach this number E. And the XY chart's already made here. So if you look at this XY chart, we see that H gets larger and larger and larger, and this chart stops at 10 million. So when H gets to 10 million, we start to get a number that starts to repeat itself, 2.718. You see it here at 10,000, 2.718, 2.718, 2.718, and the decimal runs on and on and on. So this is kind of like pi. Pi is 3.14, and of course the decimals after that run on and on and on forever. So for E, we approach the number 2.718. And again, it is called the natural exponential number. So it's actually pretty awesome what it can do. Okay. So in other words, E is the number that the expression approaches as H becomes infinitely large. We saw that by the chart. As H gets larger and larger and larger, you start to get to 2.718, yada, 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 whatever that run-on number is. For all real numbers X, the function defined by E to the X is called the natural exponential function, where the base of E is approximately 2.718 with the run-on decimals afterwards. Okay. So with that being said, let's go ahead and calculate E. All right. What calculators are you using? Are you using Desmos?
I'm using a TI-83.
TI-83? Okay. So in order for you to find E, you're gonna have to type in you're gonna have to hit the second button. Hit second, and then you're gonna have to find the button that says LN.
LN.
So second LN, it should be on the left side of your calculator, maybe 2 or 3 buttons below the second button. So you'll see 2 capital letters LN, and on the background, it's gonna say E to the X. And once you hit that, it's gonna give, it's the 83. So it's either gonna give you E to the caret or E to the empty box.
Yeah, I have E to the caret with a parenthesis.
Okay, cool. So if you have that, then all you have to do is hit, or actually be proper, it starts with a parentheses. You'll type 4 and close parentheses.
Cool.
And I can do it on Desmos, of course, a lot faster. E to the 4th. And did I say it round to 3 digits? Okay. So this means that E to the 4th is 54.598. All right, and do the same thing here. E to the negative 3.7. So I have E raised to the negative, and for your calculator, make sure you hit the negative button, not the subtract button. Hit the negative button. So negative 3.7. And you'll get 0.025. There we go. That's 3 digits, right? 0.25. Okay. And then next one, you'll type this in just as you see it. So 25, still on that one. 2,500 E raised to the 0.6. And we get 4,555.297. Okay. And that's calculating the expression, the exponential expression with the base of E. Any questions on that? Did you get it all figured out on that calculator? Okay.
Oh yeah. Sorry, I was on mute. Yeah, it's
You're
nice
good.
and easy. I like when I can use my calculator to do most of the work.
All right. So now we have one more exponential property. So this exponential property is called the equality property. This says if you have a to the m equal to a to the n, if the bases are the same, then you can set the exponents equal to each other and solve for x or whatever variable we are given. So this is the equality property for exponents. If the bases are the same, set the exponents equal to each other and solve. Okay. So we start with number 7. Here we have 2 to the x minus 4 and 2 to the 3x plus 7. Well, by using that equality property, we see that these bases are the same, which means you can set the exponents equal to each other. So I'll get x minus 4 equal to 3x plus 7. And all we have to do now is solve for x. All right, I'll move 3x over. So I'll say minus 3x, and in the same move, I'll add 4, and we're gonna get negative 2x equals 11. Then divide by negative 2, and x equals negative 11 halves. So if x is a negative 11 halves, then that is the value that will make both sides equal to each other. All right, all good?
Yeah, getting a little more complicated, but still with you.
Now we're solving, right? No calculator work now, right? Okay, number 8, 3 to the 2x equals 27 to the x minus 1. And remember, we need to have the same base on both sides. But for this problem, we don't. So what we want to do is look at 27 and ask ourselves, can you write 27 as a base of 3? So for this, you have to think of powers of 3. So 3 to the first is 3. 3 squared is 9. This means 3 cubed is what?
27.
27. So this says that, well, if we don't have the same base on both sides, we can take 27 and make it into a base of 3. So this means that this will become, the left side stays the same, 3 to the 2x, and 27 is now 3 to the third. But since we rewrote it, whatever this exponent is, we'll multiply the original exponent that was there. So you're going to get 3 to the third times x minus 1. Okay. And now we have the same base on the left and right side. So we can set the exponents equal to each other now. So we'll get 2x equal to 3 times x minus 1. Solve for x. That means distribute the 3. 3x minus 3. And then I'll move the 3x over to the left side. And we'll get negative x equals negative 3. And then all we have to do is divide by negative 1. And x equals 3. All right. So from that problem, if the bases are not the same, see if we can rewrite the base so we can use that equality property on both sides. Okay. All good?
Yeah.
All right. All right. Number 9, same thing. 9 to the x minus 1 equal to 27. Again, these do not have the same base on both sides, but what we learned from the last problem is now they share the common base of what?
3.
3. Good. So I'll write it here again. 3 to the first is 3. 3 squared is 9. 3 cubed is 27. Okay, so this means that 9 will be rewritten as 3 to the second. And remember that that 2 is going to multiply the exponent that was there already, the x minus 1. And 27 becomes 3 cubed. We now have the same base on both sides, which means you can now set the exponents equal to each other. So 2 times x minus 1 equal to 3. Solve for x. I get 2x minus 2 equal to 3. Add the 2 over. And 2x equals 5. Divide by 2. And x equals 5 halves. There we go. And that is simplifying using the new exponential property of equality. So again, if the bases are the same on the left and right, set the exponents equal to each other and solve. If they're not equal, we'll see if you can change a base into a common base, as we did for 8 and 9. Okay. Whew. All right. Those are fun. Any questions on those 3?
No, sir.
right. Okay. So when we were talking about the number E earlier, and I said it deals with exponential growth and exponential decay. So it can tell you the rate at which a population is growing or the rate that they are decaying, or it can tell you the same with money. It can tell you the rate that your money is growing in an investment or the rate that your money is decreasing in an investment. And here are some formulas that use the base of E. So these are called exponential growth formulas. So for the first one, y equals c times e to the kt. C is the initial amount. So let's say that, I guess it's easier to talk about money. Let's say we put 10 bucks in. That would be the initial amount. And after X amount of years or T amount of years, we would want to know how much money our 10 bucks has made in investments. So C is the initial amount. K is the growth rate. So if K is greater than 0, then this is a growth rate. And for money, that's a good thing. T is always time, and Y is the final amount. So these three problems all share similar, properties. They're basically the same equation. They're just used in different formats for different problems. The next one says n equals n initial times e to the kt. Well, guess what? N initial is the initial amount. That's how much money you've put in the first time for your investment. K is still the growth rate, T is still time, and N is still the final amount. And then the third one, this one's most commonly used for decay. Like I said, you can find the decay rate of a certain population of animals. You can find the decay rate of your investment. You can also find how old a dinosaur is by using this formula. So it's all works together, science, nature, and business. But I think we're all more worried about the business. So A initial is again the initial amount. K is still the growth rate. T is time, and A is the final amount. So these are basically all the same formula. They are just used in different types of problems. Okay. And the only time you'd have an exponential decay is if K was less than 0. So if K is less than 0, then that is a decay rate. Okay. So with that being said, 10. An exponential population model for Ethiopia in 2008 was P equals 83 times e to the 0.032 t, where t is the years since 2008. Does this model represent growth or decay? So remember that. All right, let me zoom in on that. So remember, in this form, you're going to P equals, I'll say C E to the K T. So if you compare this equation with this one, what's our K value?
.032.
There you go, 0.032. Is that positive or negative?
Positive.
Positive. So that would represent a growth.
Growth.
Good. So it's positive. Good. Okay. And then next, it says, using this model, what is the predicted population for Ethiopia in the year 2020? Okay. Well, what are we going to plug in for T?
Years past.
Years, good. So years past 2008. So if we want to know in 2020, well, what's the difference?
12.
12. So that's the number that goes in there. And again, I'll use Desmos. Why not? And for your calculator, you type it in just like that. And for Desmos, I'd type it in just like that. Oh, well, actually for yours, since it gives you the caret, so for your TI 83, you're gonna type 83, you're gonna do the E button, and it does the caret. So what you're gonna do is have everything in parentheses. You're gonna do 0.032 times 12, and then close your parentheses. So that's how you'll type it in.
And I put the 83 before I.
Exactly.
Yeah.
For Desmos, it lets me type it in all just like that. And here we get 121.8. I'll round to 2, 6. So I'm pretty sure we're not given a number here, but I'm pretty sure this number has to be in the what? We're talking about population.
In the millions?
At least in the millions. I don't think 1 billion people live there, but I don't know. All right, cool. So that's how you type it in. All good?
Yes, sir.
All right. All right, last page. Let's talk about compound interest, which of course we'll get into later. Chapter 3 is all about money and lots of formulas. Okay, so some terms. Interest is of course the fee paid to use another's money. Interest rate is computed as a percent of the principal over a given amount of period of time. And compound interest is interest paid on interest reinvested. So this formula is very useful in finding out how much money you'll have after you've invested it one time over a certain period of years. So just over a certain period. It also tells you how much money you'll owe if you take out a loan over a certain amount of time. Okay, so for this formula, A equals P times 1 plus R over M to the MT. A is the final amount of money. P is the present amount. It's either the amount you invested or the amount you borrowed. R is the rate. M is the number of compoundings a year. So M, it's going to say that you're borrowing this money or you're investing this money and it's getting compounded daily, weekly, monthly, all within a year. So M is the number of compoundings within a year. And T is time in years. T is always in years. If T is not in years, you must convert it to years. Okay. So maybe I can just minimize. Okay, that's fine. I'll be back to Desmos when we calculate. Okay, so let's try this formula out. If $1,000 is invested in an account paying 10% compounded monthly, how much will be in the account at the end of 10 years? Round to the nearest cent. Okay, so for this one, let's just go ahead and label everything this problem is giving us. Sorry, get that. Okay, so it says our initial investment is $1,000. So that's going to be P. P is $1,000. And then it says the rate is 10%. So remember, for rate, you always convert it to decimal. Always convert to decimal. And then it says we are compounding monthly. How many months are in a year?
12.
12. Good. And we want to know how much will be in the account at the end of 10 years. So that means that time is 10. Okay, so let's put it all together. And we're going to get A equals 1,000 times 1 plus the rate 0.10 over the number of compoundings, 12, raised to the number of compoundings times time. So raised to the 12 times 10. Okay. So for me, since I'm using Desmos, I can type it in just like this. For your TI-83, oh boy, classic input. It's going to be 1,000. You'll start your parentheses. You'll do 1 plus 0.10 divide 12, close parentheses. And then you'll hit that caret button. And after you hit the caret, it's going to be parentheses 12 times 10, or you can type in 120. And that'll give you the answer.
Word.
All right, so let's try it out. All right, so I'm typing this in. So 1,000 times 1 plus 0.10. Oh, too many zeros. 0.10 divide 12, all raised to the 120. Or I could even say 12 times 10. Oh, not there. Keep it as an exponent. Maybe it's better just to type 120 then. There we go. Okay, so what this problem says is that after investing $1,000 at 10% interest for 10 years, where your money makes interest every single month, you will only come out with $2,707.04. That sucks. That means it took you 10 years to make how much money?
$3,000 short.
Well, this is an investment. So if we end up with 27, I mean, we're short of 3,000, but it took us 10 years to make $1,700.
Yeah.
So that tells you how to invest smarter. You just don't want to put $1,000 in and let it sit. You want to put $1,000 in every month if you can. You want to put $1,000 in every 2 weeks if you can. So that's how investing works. The more you put in, the more you're gonna get. Unless the stock market crumbles and we're all out of luck.
Knock on wood.
Yep. Okay. Number 12. We are using a new formula now, which is at the top there. It's called continuous compound interest. The formula is A equals P times E to the RT. So this formula, I like to call it PERT. So again, P is the beginning investment, E is your exponential base, and then R is your rate, and T is for time in years. So the difference between this formula and the one we just used is that PERT uses continuous compound interest. So this means that your money is making money every second, every minute, every hour, every day for T amount of years. Yes, it sounds marvelous, but it's only marvelous if you have a wonderful rate that you are investing at. If you don't, then your money's just going to build really, really, really slow, continuously. Doesn't even sound like it makes sense, right? All right. So for this problem, we're investing $1,000. And it's going to an account paying 10% compounded continuously. So the rate again is 10% or 0.10. And then it says how much will be the account at the end of 10 years. So T is time, 10 years. So whenever you see the words compounded continuously, you will always use PERT. So if you see those words compounded continuously, always use PERT. Okay, now let's plug it all in. A equals 1,000 times E to the rate times time. So to the 0.10 times 10. Okay. And of course, for your input, you'll do the same, except all you have to do is put parentheses around that, which is probably the same thing I'm gonna have to do here. So let me see. 1,000 E, and then to the parentheses, why not? Builds good habit, 0.10 times 10, and boom. We will make $2,718.28. Okay. So we see that if we compound continuously for the 10 years, instead of compounding monthly, we're only going to make how much more money?
$11.
$11 more.
24 cents.
That's a gain. So again, it would seem that if your money is making interest like every second, every minute, every hour, you'd be rich, but no, there is your rate that you have to deal with. And of course, other factors at play, but yep, that is compound interest and continuous compound interest. And we'll get more into these types of problems in chapter 3. We still have 2.6 to go over, and then we can start going to chapter 3. But any questions on this section?
No, sir.
Yeah, then we are done.